Hello everyone. Today let's solve the problem number 743, network delay time. So what the question states here, we are given n nodes in the network. So here we are given n nodes in the network labeled from 1 to n. So they have given here n equals 4 means we have 4 nodes. It starts from 1 to n as I have said in the question. So 1, 2, 3, 4. We have 4 nodes, right? So n equals 4 they have given here. We are given an n nodes in the network labeled from 1 to n. Each directed edge u, v, w in the times array means a signal takes w time to travel from node u to node v. So this one source node, whatever k they have mentioned, k equals 2 they have given here. In this case, k will be considered as the root always. Whatever the k they have given, k in the case this one, it represents the node, right? So here the node 2 they have given, k equals 2 they have given. So we have to consider this one. K will always be root. You have to consider this one as root, right? So k will always be root. This one, just keep this in mind. And UVW means here in the times array means here they have given this is U, this is V, this is W. 2, 1, 1 they have mentioned here, right? So U is nothing but the source node that we need to consider. This one, 1 is nothing but the target node here. This will be the source node, 2 will be the source node, and 1 will be the target node. And what is W here? W is time. Time that it takes to send the signal from source node to destination node or source node to target node here, right? Suppose if we are considering this one, because 1 is having an incoming edge from the node 2, right? So again I'll tell, just give me a second here. So here UVW means this will be the source node, this will be the 1 will be the this one target node or the destination node, and this will be the time here. In this case 2, 3, 1 same thing, 3, 4, 1 same thing you can consider here. This will be the source node, this will be the target node, U, this will be U, this will be V, and W is nothing but the time that took for the signal to travel from 2 to 1. So that's what they are given here. I hope this is clear. What we need to do here, we need to determine the minimum time for all the nodes to receive the signal when it starts from node k. So minimum time it takes for all the nodes to receive the signal. So here in this case we have to consider 1, this one 3, also 4. So 1, 2, 3, 4. From 2, node 1, node 3, node 4 has to receive the signal from 2, right? So minimum time we have to find out. We need to determine the minimum time for all the nodes to receive the signal when it starts from node k, nothing but node 2 here in this case, right? So minimum time is equivalent to the maximum path. So here you can clearly see, means maximum path here, this is having 1 and this is also having 1. This is the minimum path, right? So it is having the time 1, least number. Here maximum path is the longest path that we have in the this one, in the diagram that they have shown, right? In the graph, longest path in the graph we can consider here. This will be 1 plus 1, right? Minimum path for this one, 2 to 1, 2 to 3, directed graph they have shown here. 2 to 3 they have mentioned here 1. This will be from 2 to 3 it is 1. From 2 to 1 it is 1. But from 2 to 4 we have to consider this path as well, right? Because we have to find the minimum time for all the nodes to receive the signal. So we have to consider path 2 to 4 as well. From 2 to 3 it takes 1, and from 3 to 4 this is having the directed edge from 3 to 4. So 2 to 3 1 and 3 to 4 1. 1 plus 1 will be 2 here in this case. So the maximum the minimum time it takes for all the nodes to receive the signal will be 2 in this case, right? We are considering the maximum path, so it will be 1 plus 1 here in this case. This will be 2, right? So 2, that's what they have given in the output here. We need to display the same thing in the output. K is nothing but the from the node, the root node that we need to consider. N is nothing but the number of nodes, and this one UVW we know this is source node, this is target node, and this is time. I hope this is completely clear, right? So same goes with the example 2 and example 1. You can just visualize in the same way that I have showed for the example 2 and example 3 as well. If there are no path at all, if we cannot send the signal from that particular node, then if you don't have any path, so then we can just we have to just display the output as -1. That's what they have given here. -1 we have to display. Just keep this one in the mind, right? So let's discuss the approach. I'll just consider the same example they have shown here. The first example that I'll consider for the approach. Let's discuss the approach, and then let's discuss the edge cases one by one. Finally, after discussing edge cases, let's write the code and discuss the complexities of the code that we have written. Initially, as usual, let's discuss the approach. So here, let's discuss the approach step by step. I have just considered the same first example that they have given in the this one question, right? So here they have given times 211. This is nothing but u, v, w, right? Source node, target node, as well as the time. Same goes with 231 as well as 341. N equals 4, k equals 2 they have given. This is nothing but the root node, and this is number of nodes. This way, no, this is nothing but number of nodes here. So this is fine. So just keep this in mind. So we are going with the Dijkstra's algorithm with minimum priority queue. So we can go with we can solve this one using the min heap as well. So for the min heap, Leetcode doesn't provide built-in min heap. So we have to build this one min heap from the scratch, and then we have to make use of it in this one main function. So it will be lengthier. The process will be lengthier. So let's go with the minimum priority queue itself. So the Leetcode provides built-in minimum priority queue, right? So we can just go with the min priority queue. This one, Dijkstra's algorithm with minimum priority queue. Just keep this one in mind. So let's this one. Let's discuss this one step by step. How can we solve this, right? So first thing here is we have to represent the network as graph. So here we have done the same thing. We have we are creating we have created a directed graph from the inputs that they have given here. Node 2 to node 1 we have the time 1, node 2 to node 3 we have time 1, and node 3 to node 4 also we have time 1, right? Now let's make use of the Dijkstra's algorithm. So we'll be applying Dijkstra's algorithm to find the shortest path using minimum priority queue, right? So k they have given here 2. You can clearly see here this one. K we have been given k equals 2 here. Let me write this one again here. K equals 2 they have given. So we have to start from the k. This is root node here. We have to start from the k, right? So what we will do here, first step, we will be starting at node 2 with the time 0. Initially time will be 0. We are initializing, or we are starting at node 2 with time 0, and we will add this one to the priority queue. Initially we have to start this one, start with 2, because k we have been given 2. We are starting with the 2 initialization part. Let's move to the initialization part. We will start with node 2, means we'll consider this one, node 2, and the time taken here will be, initially time will be 0. Initially time will be 0. This is just the initialization part. We are not sending any signal. We are just considering we are starting, or we are considering the start node, this one, nothing but 2. K equals 2 we have been given here. So time will be here 0 initially. So next we have to process node 2. So we have to process node 2, means from node 2, outgoing edges of node 2 we have to consider, right? So we are processing node 2. First we are sending signal to node 1 here. You can clearly see this path. We are sending signal to node 1, and we are sending signal to node this one, node 3 here. We are sending signal to node 1, and we are sending signal to node 3 here. We have the time 1 and 1 here. Send signal to node 1, send signal to node 3. So we can write in this way, right? We are from 2 we are sending the signal to node 1. From 2 we are sending the signal to node 3 here. So time for this one will be initial time is 0 here plus 1. Why? Because we have 1 here, time mentioned here. Here for node 2 to 3 also it is 1 itself, right? This will be here, time will be 0 plus 1 here and 0 plus 1. This will be equal to 1 in this case for both, right? So this is when we process node 2 to 1 and node 2 to node 3, right? So then we have to process node 1 here. Now we have to process node 1. We don't have the outgoing edge at all here for 1. From 1 we don't have the this one outgoing edge at all, right? So here what we will do, we don't have outgoing edges at all from 1. So we will ignore this one. So let me write here 1, no outgoing edge here. So we will be ignoring this one, right? So next step, so just give me a second here. Next step, we will just come here, this one. We have to process node 3. We will be considering node 3 now. From 3, we are sending signal to node 4 here. You can clearly see we have to send this one from node 4. So we already have 1. Time is 1 because we have already sent this one signal from 2 to 3. Here time is 1 because we are considering from k. We are considering from k, right? So we already have the time 2. Then we are sending the signal to node 4. Now time was initially 1. So this one 3 to 4 we are sending. So time was initially 1 and from 3 to 4 also it takes time 1. So this will be 2 in this case, right? So I hope this is clear. Finally, we have to process the node 4 here. So just give me a second here. We have to process this one, node 4 here, this one, right? So node 4, similar to the node 1, it doesn't have any outgoing edge at all here. You can clearly see in the figure. So we don't have any outgoing edge at all. So I'll just write here 1, no outgoing edge here. This is fine. We don't have any outgoing edge at all. So time, we are ignoring this one, right? So at this point, all the nodes are reached here. 1, we can clearly see 2 to 1, 2 to 3, 2 we consider initially, 3 to 4 and 1. So at this point, all the nodes are reached. The last node that received the signal at t equals 2, this one, time equals 2, the last node, this one we are speaking of. This one we ignored this one, right? So because no outgoing edge. So the last one that received the signal at t equals 2 will be the answer here. This will be the answer. 2 will be the answer. Why? We have to consider all this one. We have to find the minimum time it took for all the nodes to receive the signal, right? This will cover. So maximum path we need to consider. In this case, the maximum path is from 2 to 3, 3 to 4. Nothing but 1 plus 1 here. In this case, 2 will be the answer. So I hope this is completely clear. The approach is completely clear. So this is the approach that we are going with. I hope the approach is completely clear. Now let's discuss the edge cases one by one. So the first edge case that we'll be discussing here is unreachable node. So I'll just give here unreachable node. This is for the condition unreachable node. Input I'll just consider here times equals let me consider 1 to 1. This one n let me give here 2 and k also let me give here 2. So output will be here in this case minus 1 because node 1 is unreachable from 2. Here node 1 is unreachable from 2. So you can just visualize in the same way that I had shown for the example 1 previously in the approach. You can just visualize in the same way. The output will be minus 1 because node 1 is unreachable from 2, right? So this is for the condition unreachable node. Let's move on to the next edge case. Nothing but here single connection. So when I say single connection here, input let's consider here times. So this will be 1, 2, 1. Let me consider here. Let me give n equals to 2 and k equals 1 in this case. So here output will be 1 in this case. The direct path is available. So output will be in this case 1. So again I am telling you can check in the same way that I had showed for the example 1. So you can visualize or you can try it out in the same way that I had showed for example 1 by drawing the graph. So here direct path is available. So the output will be in this case 1. So let's move on with the final edge case or the third edge case here. Already at destination. Already at destination. So when I say already at destination, let me consider the input here times. So here let me give empty array n equals 1 and k equals 1. So this is already at the destination. We have only one node here, right? Nodes also 1, k also we have to start from 1 itself. So it is already at the destination. So output will be 0 in this case. So we don't have edge at all here. But all the nodes are reached because k we are starting from 1. Node also we are 1 and times this is empty. So here no edges are found but all the nodes are reached. So here no edges but all nodes are reached here. This is fine. This is for the condition no edges but all the nodes are reached, right? This is for the condition already at the destination because no edges but all the nodes are reached here. The output will be 0 in this case. I hope all the 3 edge cases are clear. First one was for the unreachable node, second one was for the single connection, third one was for the already at destination. So I hope all the 3 edge cases are clear. Now let's start writing the code. So let's start writing the code. Initially, so we have to create the adjacency list representation of the graph, right? So for that one, I'll just give you let graph equals. Let's make use of the hash map here. So this is fine. We are creating the adjacency list representation of the graph here. We have discussed about this one. Let's construct the graph from input times, right? So let's now construct the graph from input times here. For I'll just give here let u v w source node, target node as well as the time of times. So this is fine. I hope this is clear. So let me write the simple if condition. If graph doesn't has the source node, nothing but u here. In this case, let's set graph. Let's update by making use of the set property u and this one empty array initially, right? So and then we have to store the edges as time and destination. So how can I articulate that one in the form of code? To store the edges as time and destination, I can just give here graph dot get. Here get has set this one, these properties. We are making use of this one, right? Hash map properties here. So graph dot get of u, I'll just give here u. So what we have to add here, we have to add the time as well as the destination. So here we know that u is source node, v is nothing but the destination, w is time. Here we are storing time and destination, nothing but w and v. So we have to add w and v right within the array. So I'll just make use of the push and I'll just give here v, w and v here. I hope this is completely clear. What we are doing in short, I can just say here we are constructing the graph from the input times here, right? So now let's come to the main part. Let's make use of the minimum priority queue for the disk algorithm. So I'll just give here PQ, nothing but the priority queue. Let's create min priority queue here. This is fine. So inside this one, let me go with the priority So let me set this one to a initially a of 0. This is fine. Source node. So source node nothing but k. K in our example, whatever we took k, they had given 2 right here for this example. So this one, initially we are setting this one to a of 0 here. This is fine, I think. So next step here is we have to store the shortest known time to each node. So that is the reason we'll be making use of the map here. So let's make use of the variable distance. I'll call this one dist and let me create here map. This is fine. I hope this is clear. Next step, let's start the distress from node k with initially time 0. We saw that one step by step in the approach, right? So we saw this one step by step in the approach. Let's implement the same thing. Let's process the nodes in priority order. Nothing but shortest known from the start, as we are making use of the minimum priority queue, right? So let's process the nodes in priority order. So here, while not of PQ is empty. So it shouldn't be empty, right? It should be having certain nodes to process. So when priority queue is not empty, we are just making use of the isEmpty property here. So let's go with here time as well as node within the array dq to remove. So we have to get the node with the smallest time, right? Means maximum path. So I have set this one. To get the minimum time, we have to go with the maximum path. So time comma node I have given here. I'll just go with the dq to remove dot element. This is fine. What we are doing here, we are trying to get the node with the smallest time here, means maximum path. So if we have already visited the node, then we have to ignore, means we only process a node once in the priority queue. So we are just processing the node once, and if that node is already visited, then we have to ignore. This we will write in the simple if condition. Let's write the simple if condition here. Distance dot has, means if we have already visited the node here of node, we will skip that one by making use of the continue keyword here, right? Simple. Next step is we have to record the shortest known time to reach this node, right? Shortest known time, nothing but the maximum path. We have to record shortest known time or the maximum path, the time of the maximum path to reach the particular node. I'll make use of set property here. Distance dot set node comma time. This is fair. Next step after this, if all the nodes are reached, so suppose if we have reached all the nodes, then we have to return the maximum time that is seen so far. Nothing but the maximum path, the time of the maximum path. That's what we need to find here, right? Minimum time that for all the nodes to receive the signal is equivalent to the maximum the time the maximum path time, right? So if all the nodes are reached, we have to return the maximum time that has been seen so far. Again, simple if condition, dist dot size, this is equal to n. Then what we will do, we will return time here. This is fine. Next step or the final step here, after doing that, we have to explore all the neighbors of the current node. We have to explore all the neighbors of the current node as well. For this one, I'll just write a for loop or let this one time as well as the neighbor. Time as well as the neighbor of, we have to get the value of the particular node, right? So I'll just make use of the get property here of node. I hope this is clear. This one, it can be neighbor can exist or it can be empty array, right? If the node doesn't exist or if the neighbor doesn't exist, it can be empty array, or I'll just give here empty array. So I hope this is clear. This is simple. Then what we have to do, we have to add to the priority queue with the updated time every step. We saw that one same. We saw the same thing in the approach, right? So we are just adding this one to the priority queue time to the priority queue with the updated time. So the signal from one node to another node with the updated time we are adding to the priority queue. That's what we saw step by step in the approach as well. So how can I articulate that one in the form of code? I'll just give here enqueue within the array. I'll just pass here time plus w and neighbor. Here neighbor. This is fine. So I hope this is clear. The final step is so what happened here? Yeah. The final step is if we cannot reach all the nodes, then we have to return -1. Or if not all nodes are reached, then in that particular case, we have to return -1. We discussed the third example here, right? The same thing. If we are not able to reach all the nodes, then we have to return -1. So let's give here return -1 here. So let me quickly format the code and let me hit the run button. I hope this works. So wrong answer we are getting. So let's check what we have done. So what mistake I have done here is, you can clearly see we are creating the new minimum priority queue. This is fine. We are setting this one. And finally, we are storing the shortest path known time to each node by making use of the map. This is fine. So we have to start the Digistra's algorithm from the node K with time 0 initially, right? That's what. That I forgot entirely, and I have written here while priority queue is empty. So initialization I have not done at all here. So we have to start the Digistra's algorithm from node A with the time 0 initially. That's initialization part. So I have to give here priority queue, PQ I have considered. So to add, I'll just make use of the NQ here. NQ 0, right? Initially with time 0 from K. So this has to be within the array we have to consider. So let me consider this one within the array. This is fine. Let me format this once and let me hit the run button. I hope this works now. I hope, yeah. You can clearly see the sample test cases are getting passed here. So let me hit the submit button now. So you can clearly see here all the test cases are getting passed here. So the code works absolutely correct. Let's quickly discuss the complexities of the code that we have written. So the approach that we went with here is Digistra's algorithm with minimum priority queue, or Digistra's algorithm with priority queue. So what would be the time complexity, or the overall time complexity here? So the overall time complexity would be here. Just give me a second here. It will be big O of E log n. So why it is big of E log n here? Because we have to process edges, right? So E is nothing but the edges and n is nothing but nodes. So due to the priority queue operations, so overall time complexity would be here log n. We know that priority queue, this one, it takes log n, and E, this is nothing but it is for the edges. So due to the priority queue operations, the overall time complexity would be big of E log n. I hope this is clear. So what will be the space complexity here? Overall space complexity would be big O of n plus E here. So when I say big O of n plus E, graph storage, we are going with the graph storage, this one, new map we are considering here. This one, as well as the priority queue. We are creating a priority queue here. This one you can see here. Graph storage as well as the priority queue makes it the space complexity big O of n plus E. I hope the time complexity and the space complexity is completely clear. So overall time complexity here would be big O of E log n, and overall space complexity here would be big O of n plus E. I hope the solution is completely clear, right? For now, this is it. Thanks for watching, guys.